Hey physics fans, today we're going to be looking at text problem 11-28 in your OpenStax text. Let's get into it. So, after reading the problem, we notice that we have a bowling ball that's going up a ramp without slipping, and it gives us the initial velocity of the bowling ball. So, we have a change in height, so there's some change in potential energy, and we're solving for a final speed, so there's some trade-off in kinetic energy. So this is a conservation of energy problem. Additionally, it tells us that the ball is rolling without slipping as it's going up the ramp, so it's a conservation of energy with rolling motion problem. Our task in the first part is to find the final velocity at the top with a given height of ½ meter. And in part B, it's to see if it even reaches the top if we increase the height to 1 meter. Now, the physics that we need is our expression for conservation of energy. Additionally, we need the link equation, because with rolling motion there's a link between our speed at the center of mass and our angular speed. And we need the expression for the inertia of a sphere, because we're going to assume that our bowling ball is a solid sphere with a uniform density. Now, drawing our problem, we have an initial and final state of our bowling ball given by the solid line for our initial state and the dashed line for our final state. In the initial state, we have some initial velocity going up the ramp, and we're going to have some initial angular velocity coming into the screen because the ball is rolling. In our final state, we're solving for the final velocity, which I've denoted in pink, and we have a final angular velocity, which is also coming in towards the screen. Now, in conservation of energy problems, we need to show where the gravitational potential is equal to 0. And the way I like to do this is by choosing the lower point between our initial and final state, which in this case is our initial state, and making the gravitational potential energy 0 for that state. Our givens, once again, it says that we're given an initial velocity, but it doesn't give us any direction, it doesn't give us any length of the ramp, so it's really giving us an initial speed. And it gives us a change in height and tells us that there's no slipping, which means that the work due to non-conservative forces is going to be 0 in this problem. Our assumption, once again, we're assuming that it's a solid sphere, and because it doesn't give us any directions, we're assuming that we're solving for the speed, not the velocity, when it gets to the top of the ramp. Let's move over to our solve step. So, when we're solving conservation of energy problems, the first thing we do is write down the equation for conservation of energy. Then we build our energy table, which is from all of the equations that are on your physics reference card under the conservation of energy equation. So, in the initial state, shown once again by our solid line and our solid sphere, we have a bowling ball that is rolling up the ramp. So, it has some kinetic energy, and because it's a rolling object, it has both translational kinetic energy and rotational kinetic energy. In the final state, shown by our dashed line, our bowling ball is still rolling, and it has some increase in height, so it has both gravitational potential energy for our increase in height, and it has kinetic energy, both translational kinetic energy and rotational kinetic energy. Now remember that change in height was based off of showing that the gravitational potential energy is 0 in our initial state. At this time, we substitute all of our terms for the final energies into our final energy, and all of the terms for our initial energy into our initial energy. We sum all of those up and write them down in our expression for conservation of energy. So the work due to non-conservative forces was 0, and then we have our final energy minus our initial energy. At this point, we need to substitute both our link equation in for the relationship between our speed and our angular speed, and the equation for the inertia of a sphere about its center of mass. And you can see we've done that for the inertia and for the angular speed. At this point, our expression starts to become a lot simpler. You can see that there's a mass variable in every single one of our energy terms. So we can divide the entire expression by the mass to simplify our equation. Additionally, in every energy term where you see a radius squared in the numerator, there's also a radius squared in the denominator from our link equation, so we can cancel those out. This simplifies our expression a lot and allows us to isolate the final speed for our equation, and that is what we are trying to solve for in our task. So now we have an algebraic expression for our final speed in terms of our given variables. When substituting all of our given variables into our algebraic expression for part A, we get 1.4 meters per second. And because our least amount of significant figures is 0.5, so one significant figure, then we report our answer as 1 meter per second. For part B, when we substitute in 1 meter instead of half a meter for the height, then we notice we get an imaginary number. So it does not make it to the top of the ramp because we've gotten an imaginary number for part B. Now let's check. Our units for our speed are in meters per second. Our significant figures are 1, because that's what we discussed. And is this reasonable? Well, it's reasonable that if we start at 3 meters per second and then we increase our height, that we would have a less speed at the top of the ramp. Additionally, it's reasonable that if we increased the height of the ramp, then the ball would not make it at all. Thank you. Have a great night.